So let's find some derivatives. Let's find the derivative of cosine to the fifth of x cubed plus 4. And so when I see this, I see a function of a function. I actually see many functions composed together. In fact, when I see this specifically, I want to do one thing before I start differentiating. I want to rewrite this as the derivative of cosine of x cubed plus 4 all to the fifth power. So that I see this as some stuff to the fifth. And when I take the derivative is going to be 5 times my stuff to the fourth, right? Leave the inside alone, take the derivative of the outside, the derivative of something to the fifth is 5 times something to the fourth, and then we have to multiply by the derivative of the inside, or the derivative of the stuff. But now I have to use the chain rule again, because the derivative of cosine of some new stuff, well, the derivative of cosine of something is negative sine of something. So cosine of stuff is going to be negative sine of that new stuff times the derivative of that stuff. And the derivative of x cubed plus 4 is 3x squared. And then you would normally put it in parentheses, but since there's only one term and there's nothing out of subtracting, we can just not use parentheses. You could also, right, it's perfectly fine to put that in parentheses if that makes you feel more comfortable, but it's not necessary. So that's how we take the derivative of that, right? Chain rule, chain rule, chain rule. Let's do one or two more. Oh yeah, there is one. I feel like, sorry, let me look at one thing real quick here. I thought, okay, yeah, there we go. Okay, so, sure. Say f of x is equal to e to the tangent of the square root of x. And I want to take the derivative, right? It's all derivatives all the time. So let me put caret in here. So again, right? I said this last class. When you take the derivative of something, I usually think of it as the outermost function first. So like here I'm trying to take the derivative of e to the stuff. And I know the derivative of e to the x is e to the x. So the derivative of e to the stuff is going to be e to the stuff times the derivative of that stuff, which maybe I'll just write as the derivative of tangent of root x for a second. And now I have to actually find the derivative of that. So that's going to end up being e to the tangent of the square root of x times, all right, I know the derivative of tangent of something is secant squared of that thing times the derivative of that thing. So the tangent of, I'm going to say this is x to the 1/2 in my head so I can differentiate it more easily. The derivative of tangent of x to the 1/2 is secant squared of x to the 1/2 power times the derivative of that, which is 1/2 x to the negative 1/2. And again, I would not simplify this unless someone asked me to. I would leave it like that. E to the tangent of the square root of x times secant squared of the square root of x times 1/2 x to the negative 1/2. That would be fine. Again, please pipe in or chime in if you have any questions. I don't know if we've talked about this or if you've talked about this in your class yet, but what about the derivative of g of x equal to 4 to the x? So here's the thing. 4 to the x is a lot like e to the x. I know the derivative of e to the x is e to the x. The derivative of 4 to the x is going to be kind of just like 4 to the x, except there's a little bit more. There's a couple different ways of doing this. Typically in the 17 series, people often do the following thing. They say, I'm going to rewrite 4 to the x. I'm going to rewrite, and this is definitely, you should pay attention here for sure. I'm going to rewrite 4 to the x as e to the natural log of 4 to the x. And then I'm going to use the logarithmic rules to say, oh, natural log of 4 to a power, I can bring that power down in front of the logarithm. and say that this is actually equal to e to the x times natural log of 4. I can take a look at that. Sure. Let me. Yeah. So now I'm going to take the derivative, right? So just like here, right? The derivative of e to the stuff is e to the stuff times the derivative of the stuff. I'm going to do the same thing right here. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. Chain rule. Chain rule all the time. Chain rule all the time. So the derivative of e to the stuff is e to the stuff times, all right, what's the derivative of x times natural log of 4? Well, that's just x times a constant. Right? I think we talked a lot last time about a natural log of a number, or maybe that's like, sorry, I really confused which class, what I said which class. I will just say natural log of a number is just a constant, right? If you plug in natural log of 4 to your calculator, you get something like 1.38, I think. I don't know, let me check. Natural log of 4, yeah, 1.38 approximately. So that's a constant. And the derivative of x times a constant, what's the derivative of 8x? Oh, that's just 8. The derivative of x times a constant is just the constant. So the derivative of x times natural log of 4 is just natural log of 4. And although we could leave it like this, we typically don't. What we usually do is we remember that, oh, wait, e to the x natural log of 4 is just e to the natural log of 4 to the x, which is really just 4 to the x. So we actually go back and say, well, I should really replace this original thing with what it was actually equal to, which is 4 to the x, so that we can write this as 4 to the x times natural log of 4. So here's what we see. The derivative of 4 to the x is natural log of 4. The derivative of 4 to the x is 4 to the x times natural log of 4. And generally, if you have a base that's not e raised to a power that is variable, the derivative is like it would be if it was e, except it's the base you have times the natural log of the base. So we could also say, so the thing is, I don't want to do this like every time I have a different base. So while we certainly could, like if I want to find the derivative of 2 to the x, I could rewrite it as the derivative of e to the natural log of 2 to the x, and then say that's the derivative of e to the x times natural log of 2, and then the derivative of e to the stuff is e to the stuff times the derivative of stuff, and the derivative of x times natural log of 2 is just natural log of 2. But then this is just 2 to the x, so we end up with 2 to the x times natural log of 2. Generally, we have this same pattern for any positive base. It's not 1, where the derivative of a to the x is equal to a to the x times the natural log of a. And it even does work if your base is e, right? If your base is e, the derivative of e to the x is equal to e to the x times the natural log of e. But the natural log of e is just asking you e to what power equals e, and that number is 1. So this is just e to the x times 1, which is e to the x. So there's two ways of thinking about it. Well, I should say there's two different. There's 4 ways of thinking about it. So here are the 4 rules for exponential derivatives I think you should kind of know. Really, they all come down to one big rule, but there's kind of 4 smaller versions. So I'm going to write some of the same things I just wrote. The derivative of e to the x is e to the x. The derivative of e to the stuff, like e to the f of x, is e to the f of x times the derivative of f of x, or e to the stuff times the derivative of stuff. I should point out, just in case you were curious, this derivative of stuff is not in the exponent, right? It's e to the power of your original stuff, and then not in the exponent times the derivative of that stuff. And then if your base isn't e, there's a similar version for each of these. The derivative of a to the x, where a is a positive base, is a to the x times the natural log of a. And the derivative of a to the stuff, well, it's going to follow the same sort of rules, right? The derivative of e to the stuff is e to the stuff times the derivative of the stuff. The derivative of a to the stuff is going to have the same sort of thing happen, except you're also going to get the natural log of your base showing up. So it's going to be the derivative of a to the stuff, well, the derivative of a to the x is a to the x times the natural log of a. So the derivative of a to the stuff is a to the stuff times natural log of a times the derivative of the stuff. That's what's happening there. So that's what I would encourage you to remember. For example, we could ask the question, what's the derivative of f of x equal to 2 to the cotangent of 3x? All right, so my function is 2 to the stuff. My derivative is 2 to the stuff times the natural log of 2 times the derivative of the stuff, which I don't have enough room to write because, well, maybe I do. Times, let me smoosh things together just a little bit. 2 to the stuff times the natural log of 2 times the derivative of the stuff, which is the derivative cotangent of something is negative cosecant squared of that something. So it's negative cosecant squared of 3x times the derivative of 3x, which is just 3. And that's how we do it. And we could simplify that if we wanted to. That's not really the point here. Or what about if we were taking the derivative of, say, let's do this on the other side. I don't have enough room, really. Oh, to live in the glory days when I had giant boards at my disposal. Oh, well. Someday. We'll be back in the classroom again. Someday. So let's see. Let's look at g of x equal to 10 to the x times cosine x. All right. So again, the derivative of some base to some stuff is the same base to that stuff times the natural log of that base times the derivative of the stuff. So here g prime of x is going to be 10 to the x times cosine of x times the natural log of 10 times the derivative of x times cosine, which is going to require the product rule. So it's going to be derivative of x times not derivative of cosine plus x times the derivative of cosine, which is negative sine of x. And yes, it's times all of this in parentheses. Okay. Nope, mouse still doesn't want to work because it hates me. Yeah, we should do this example. So here, again, when I'm thinking of the chain rule, I'm really just like, okay, I've got a function of some stuff. The derivative is take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. But sometimes people are going to ask you questions where you have to kind of actually know the chain rule like as it's written. So let me go ahead and write it up here. So I typically think of it as the following, right? So if you've got some composition of functions, f of g of x, the derivative of that is the derivative of the outside function. Leave the inside function alone. So f prime of g of x times the derivative of the inside, which is g prime of x. And you can even, right, so I'm showing this for a composition of just 2 functions, but you can actually compose a bunch of functions, right? You could say, like, if I've got f of g of h of x, and I want to find the derivative of that. So again, we kind of just keep going one layer in each time. So start with the outside. I've got f of some stuff. The derivative of f of some stuff is f prime of the stuff times the derivative of the stuff. So it's f prime of the inside, which is g of h of x, times the derivative of the inside. So I have to do the derivative of g of h of x. But to do the derivative of g of h of x, I have to use the chain rule again. So I have, okay, it's f prime of g of h of x times, okay, the derivative of g of h of x, well, take the derivative of the outer function, leave the insides alone, multiply by the derivative of the inside. So it's g prime, right, derivative of the outside, evaluated at the inside left untouched, times the derivative of the inside. And you could do this literally as many times as you wanted to. Let me actually go look at one thing real quick. section 3.5. So let's see. If someone asked a question, I want to see if it might actually fit right in with what I'm saying. Let's get there. Sure, I can totally look at that question that was asked. So someone asked for number. Actually, but let me do the thing I'm going to do first, and then I'll go to the question 35 in section 3.5, which actually is very much an example. No, I can find it. Yeah. So the thing I wanted to say is the following question. So let's say we were given this information. Suppose that we know that h of x is equal to f of g of x, and capital K of x is equal to g of f of x. And we also have this table of values. So I'm going to draw real quick like 1, 2, 3, 1. Sure. So I've got x. F of x, I've got one more column, sorry. X, I've got f, g, f prime, and g prime. And I've got the values of x are 1, 2, and 3. The values, of course, on the f values are 3, 1, and 7. The g values are 2, 8, and 2. The f prime values are 4, 5, and 7. And the g prime values are 6, 7, and 9. So what this is saying, right, is that, like f of 1 is equal to 3, and g of 2 is equal to 8, and f prime of 3 is equal to 7, and g prime of 1 is equal to 6. So that's what this table is telling us, right? It's not telling us all the derivatives everywhere, it's just telling some stuff. So I want to find two things. I want to find h prime of 1 and k prime of 1. And the idea here is that you have to know the formula version for the chain rule. You can't just say, well, okay, k prime of 1 is so really I'm trying to find this, right? I'm trying to find, well, in fact, let's start with h prime of 1, not k prime of 1. So to find h prime of 1, I have to find the derivative at just x. So what I'm really being asked to find is, I want to find h prime of x. Okay, well, I know the chain rule, right? The derivative of h is the derivative of what h is equal to. I'm trying to find the derivative of f of g of x, which we just said, right? Differentiate the outer function, leave the insides alone, times the derivative of the insides. And now that we actually know what h prime of x is, we're going to write h prime of 1. So h prime of 1 is going to be, well, I'm just going to plug in a 1 for the x. So I'm going to get f prime of g of 1 times g prime of 1. And now I'm going to look at the chart to see what's what. So let's do it this way. So g of 1 is 2, so meaning f prime of 2 times g prime of 1 is 6. And then f prime of 2 is 5. So I get 5 times 6, which is 30. And we can do the same sort of thing for k prime of 1, right? K prime, so k prime of x is going to be the derivative of g of f of x. So that's going to be g prime of f of x times f prime of x, right? Again, differentiate the outer function, leave the inside alone. I'm going to say this like a billion times. Differentiate that side, leave the inside alone, times the derivative of the inside. Okay. Don't get sick of hearing it. It's okay. So that's going to be g prime of f of 1 times f prime of 1. F of 1 is 3. So I want g prime of 3. G prime of 3 is 9 times f prime of 1 is 4. So that's how you do a problem like this. It's a little contrived, but it does get to the point of like, oh yeah, you kind of actually have to know this formula to do this thing. Yeah. So let's take a look at question 35 from the textbook. Oh yeah, it's not too terrible. I'm going to change it up. No, I'm not going to change it up. So sometimes you just have a lot of, like you can have a problem where you had to do 4 or 5 or 6 applications of the chain rule, depending on how many nested functions you have. So let's see. 35 is, I want to find the derivative of y equal to cosine of the square root of sine of tangent of pi x. One thing I will caution you against is I've seen way too many people make mistakes doing the past. I've definitely seen people say that this is a product rule, that they've mistakenly said, oh, that's cosine of x times the square root of sine of tangent of pi x. It's not, because I don't have a cosine of x, right? I have a cosine of, oh, there's nothing after it except for all this, so it's cosine of all of that. So, right, you have to have a cosine of something. And in this case, it's cosine of all that jazz. Before we differentiate, I really strongly recommend turning all of your roots into powers. So I would rewrite this as cosine of sine of tangent of pi x to the 1/2 power. So we have to work, at least I have to work from the outside in. I saw someone on one of the quizzes in one class do it from the inside out, which seemed super cool, but I was like, no, I couldn't do that. I wouldn't know how. So I'm gonna work from the outside in. My outermost function is cosine. Right, I've got cosine of some stuff. So my derivative, y prime or dy dx, whatever way you want to write it, is going to be, well, derivative cosine of some stuff is negative sine of that stuff. So negative sine of all of that left alone. So sine of tangent of pi x all to the 1/2 power. So this, I really do like the brackets there to kind of differentiate what's going on. Times the derivative of that stuff. So I have to multiply with the derivative of all of this to the 1/2 power. And so that, I'm actually kind of giving it away right there, right? That's saying that, oh, for this next derivative, we have to take the derivative of all this. The outermost function of this stuff is the 1/2 power. So the derivative of sine of tangent of pi x to the 1/2 is, well, I've got some new thing, sine of tangent of pi x, all to the 1/2 power. So my derivative is going to be 1/2 times that new thing, all to the negative 1/2. So I'm going to 1/2 times all this grossness, sine of tangent of pi x, all to the negative 1/2, times the derivative of that new thing. So now I have to take the derivative of sine of some new thing. So what's the derivative of sine of some stuff? It's cosine of that stuff. So times cosine of the new stuff, tangent of pi x, times the derivative of the new stuff. What's the derivative of tangent of pi x? Well, the derivative of tangent of the last new thing is secant squared of the last new thing times the derivative of that thing, which is pi. Holy smokes, that's a lot of chain rules. But you just keep working in one level at a time, right? At this stage, the outermost function was cosine. And then when I was taking the derivative of this part, the outermost function was the 1/2 power. And then when I was taking the derivative of this part, the outermost, in fact, let me just underline here. When I was doing the derivative of this part, the outermost function was the sine. Then when I was doing the derivative of this part, so right, the derivative of sine of some stuff was cosine of the stuff. And then when I did the derivative of the stuff, the derivative tangent of something was secant squared of something. But then I had to do the derivative of that something, which was pi. It's a lot. It's a lot of chain rules. But that's a chain rule, right? You just keep doing it until you get to a place where the thing you're taking the derivative of is just, oh, the derivative of pi x is just pi. I don't have to use the chain rule for that because I have a rule for taking the derivative of pi x. Okay, that was a lot. So let us move towards implicit differentiation, which I'm going to say probably 1,000 times is really just the chain. Implicit is just another way of using the chain rule. It's a little different in its execution sometimes, but really it is just chain rule all the time. I've kind of got that song, the party all the time song. It's like, man, party all the time, party all the time, party all the time. but it's chain rule all the time, chain rule all the time, chain rule all the time. I know it's not good, but it's what's in my head, so you know. Anyway, let's talk about the implicit differentiation. So I'm going to start off with an example that's a little maybe not quite super chain rule-y, implicity. Well, let's look at this. Suppose we want to find the derivative of the following. Y equal to x cubed plus 7x plus 1 to the 10th. Plus e to the x plus sine x plus 4 to the 8th. Plus x to the 13th power. All right, so we could totally do this straightforwardly, right? I could be like, okay, I'm gonna use the chain rule here, derivative over there, fine. But I'm gonna do something to make this look less terrible, which is not normal, but it's something I'm gonna do anyway. I'm gonna let u equal this part right here, the x cubed plus 7x plus 1. I'm going to let w equal this stuff right here, e to the x plus sine of x plus 4. And then I'm going to rewrite this so it's easier to write. I'm going to write it as, well, I can say that y is equal to u to the 10th plus w to the 8th plus x to the 13th. But it's still implied that u and w are functions of x, even though I'm not actually writing it in here. Right? I could write u of x to the 10th and w of x to the 10th if I wanted to be a little bit more explicit about their relationship, but it's not really necessary. So now I'm going to take the derivative of this stuff. So I don't want to use that pen. Take the derivative of dy dx. I'll look at one thing real quick here. Sure, yeah, okay. So what's the derivative of u to the 10th?
10u to the power 9.
And that is most of it. Let me say it a different way. What's the derivative of some stuff to the 10th? It's 10 times my stuff to the 9th times
u prime.
Should I say that one more time?
U prime?
Yeah, I'm gonna write du dx, but yes. U prime or du dx, exactly. Same deal is going to be true for w to the 8th. The derivative of some stuff to the 8th power, right, where that stuff is a function of x, is 8 times my stuff to the 7th power times the derivative of that stuff. And the derivative of x to the 13th is going to be 13x to the 12th. If you wanted, you could say, well, the derivative from stuff to the 13th is 13 times stuff to the 12th, and then you can multiply by the derivative of my stuff, but the derivative of x with respect to x is just 1, right? The derivative of x is just 1. This is just 1. Because a lot of people are like, why don't we use implicit for the x part? Well, because x is the variable we're differentiating with respect to, so we don't need to. So the x parts just work fine. And then we're going to replace u with what it's equal to. And du dx is what it's equal to. So this is going to be 10 times u to the 9th times du dx, which is 3x squared plus 7, plus 8 times w to the 7th, times the derivative, so times dw dx, which is e to the x plus cosine of x, plus 13x to the 12th. And not that we, in regular implicit differentiation, we don't usually like go back and plug in what something is, but this is the real idea here with implicit, is that we're going to have expressions where variables that aren't x are implied to be functions of x. And so when we differentiate things like u to the 10th, we get 10 u to the 9th times the derivative of u. Or w to the 7th, or to the 8th, we get 8w to the 7th times the derivative of w. So basically, whenever you differentiate something where you have a function of x implicitly, you have to multiply by the derivative of that function of x. Okay. So let's look at another kind of example that's going to ease us into this implicit stuff. This is kind of a very standard example. maybe you've already seen. Maybe not. It's a standard example in my mind anyway. So let's look at, I want to find the slope of the line tangent to the circle x squared plus y squared equal to 25 at the point 3, negative 4. I will point out that circles definitely have tangent lines, and circles are also not functions, right? The circle is not a function, it fails the vertical line test. Here's my circle. It's got a radius of 5, centered at the origin. I'm looking at the point 3, negative 4. So I'm asking, what's the tangent slope of the tangent line right about there? Sure, tangent line. Yeah, that's definitely tangent right there. Okay. So what's the slope here? Well, it looks like it's positive. I'll just give us that. So there's two ways we can do this one, because this one we can solve for y, kind of. So if I start solving for y, I get y squared equal to 25 minus x squared. If I take the square root of both sides, I get y equal to, well, I'm actually missing something. Y is plus or minus the square root of 25 by x squared. So the bottom half of the circle, that's the minus part. And so this part here is y equal to negative square root of 25 minus x squared. And this part up here is the positive part where y is positive. That's y equal to positive square root of 25 minus x squared. Right, not a function. We can't just write y as a function of x in one go. Okay? And now we're going to differentiate. So again, we're using, since we want to find the tangent line for the bottom part, we're going to use the bottom part. So we're going to use the part where it's negative. So then our derivative of y equal to negative square root of 25 minus x squared, which I meant to write as negative 25 minus x squared to the 1/2 power. Let's find the derivative there. So dy dx is going to be negative 1/2 times my stuff to the 1/2 minus 1 is negative 1/2 power times the derivative of the inside, which is negative 2x. I can cancel the negative 2 with the negative 1/2, and I can rewrite this as x over 25 minus x squared to the positive 1/2 power, or x over the square root of 25 minus x squared. And then I can plug in the point where x is equal to 3. If I plug in x equal to 3, I get that the derivative dy dx is equal to 3 over the square root of 25 minus 9 is the square root of 16, which is 4. So I get a slope of 3/4, which that looks like it could be a slope of 3/4. It's definitely positive, so we're good. But there's an issue here. Well, there's kind of an issue here. One, I had to think about which piece of the circle I actually need to use, right? I could have accidentally picked the wrong piece. And two, we're going to encounter other expressions, equations, where you can't actually solve for y as a function of x. So there is another way. Instead of solving for y, I'm going to just take the derivative of both sides of this equation, assuming or implying that y is a function of x. It's not exactly a function of x, but it's close enough to a function of x that we can still use the rules in the same sort of way. So here's what I'm going to do. And I'm going to run out of room. I'm going to erase the circles. What I'm going to do. I'm going to say, well, let's just take this equation, x squared plus y squared equal to 25. And let's differentiate both sides with respect to x, right? We're still trying to find the slope of the tangent line, but still differentiating with respect to x. I'm going to find the derivative with respect to x of both sides. Okay, so help me out here. What's the derivative of x squared?
2x.
Thank you. just reading this thing here, like, this board is for use by the AATC tutors, and don't remove it, and I did. Oh, all right. This answer is going to be slightly different. What's the derivative of some stuff squared?
2y prime.
Right. 2 times that stuff times the derivative is, I'm going to write dy dx, but usually I would write y. But usually I would write y prime. But you can use whatever notation you want, as long as it's correct. And what's the derivative of 25? 0. And now we can solve for dy dx, right? Our goal was to find the derivative. Let's find the derivative. So let's see. Dy dx, so 2y dy dx is equal to negative 2x. And then dy dx is going to equal negative 2x over 2y. So we're going to get the dy dx is equal to negative x over y. And if we plug in the point 3 for x, negative 4 for y, we get negative 3 over negative 4, which is positive 3/4. So we get the same answer. And in my mind, it's much easier to just differentiate both sides and solve for y prime, even though or for dy dx, either way, even though my answer is going to have y's in it, than it is to do that. Now, in this example, if you really wanted to, you could go back and substitute in that y is equal to plus or minus the square root of 25 minus x squared, so that you could actually write it, and you would get the same answer, right? You would be getting negative x over plus or minus the square root of 25 minus x squared, which would be this answer if you have the right piece.
Why would you have dy times dx for 2y?
Whoa, say that one more time.
You had 2y times dy dx. Why would you have the dy dx?
Well, because of the same reason on the other side, that when I multiplied, when I took the derivative of u to the 10th, I got 10 times my stuff to the 9th times the derivative of my stuff, right? I'm taking the derivative of some stuff to the 10th power, some stuff that's a function of x, and I'm using the chain rule and saying that the derivative of this stuff to the 10th power is 10 times this stuff to the 9th power, right? Take the derivative of the outside function, leave the inside alone, then you have to multiply by the derivative of the inside stuff with the chain rule. That's what's happening over here. Here we're saying, oh, y is a function of x. We are implying that y is a function of x. So when we take the derivative of some function of x squared, we're going to use the chain rule and say, oh, the derivative of something squared is 2 times something to the first power, right? The first power there. But then you have to multiply by the derivative of the insides. Sometimes, in fact, let me do one more thing here just to kind of make it extra super clear. Another way to think of it, although it takes a little more writing, but it's essentially the same, is to say, well, I'm going to write y literally as a function of x. I'm going to write this as x squared plus function of x squared equal to 25. And then when I differentiate both sides, the derivative of x squared is 2x. The derivative of some function squared is 2 times my function to the first power times the derivative of the inside part, equal to the derivative of 25, which is 0. That's the same as this, right? It's 2x plus 2 times y to the first times y prime equal to 0. So hopefully that helps clarify things. But the idea here, going forward for all the rest of these implicit problems, is that we are implying that y is a function of x. And so whenever you take the derivative of like y to the 5th, you're going to get 5 times y to the 4th, but then you have to multiply by the derivative of the inside function y, which is y prime. What ends up happening, like, so the shorthand you can kind of think of for that is that whenever you differentiate something with a y in it, you're almost always going to have to multiply by y prime. And that usually works without fail, although sometimes it can kind of get you into the wrong spot. So I really encourage all of you to think of it as, oh, I'm just using the chain rule, right? Y is my stuff always. X is just my variable. Y is the function of that variable or some stuff. And we'll do this example and then I'll show you kind of how I might think of it. So let's find dy dx or y prime. I'm going to write y prime because y prime is easier to write for the following. For the following equation, x cubed plus y to the 4th plus tangent of y equals e to the y plus sine of x. That will tell you, after the first step of this problem, the rest is just kind of terrible algebra. The first step, we use calculus to differentiate, and the rest of it is just like, okay, I'm going to do all the algebra in the world. So we're going to differentiate both sides. So I'm going to take the derivative of all of this, which I usually don't write this step, right? I would just take the derivative. I really want to be explicit about what I'm doing. Taking the derivative of this side. Okay. Derivative of x cubed is 3x squared. Because x is just our variable that we're differentiating with respect to. But the derivative of y to the fourth, or some stuff to the fourth, is going to be 4 times my stuff to the third times the derivative of the stuff. Plus, the derivative tangent of some stuff is going to be secant squared of the stuff times the derivative of the stuff, equal to the derivative of e to the stuff is e to the stuff times the derivative of the stuff. So the e to the y is e to the y times y prime. And the derivative of sine of x is going to be cosine of x. Are there questions about what I've done? It's really okay if you have questions. Like, it's always okay if you have questions, but yeah. One way you could imagine this, if you're kind of struggling with this, why have I all done my y prime stuff, is just to actually make y a function of x for a second and say, well, what if instead, and so I'll accelerate that. What if instead I was taking the derivative of, like x cubed plus, I'm going to make y some not too terrible function of x, like x squared plus 1, plus tangent of x squared plus 1. Right, I'm just replacing y with x squared plus 1 just to kind of show you something. Right, so the x squared plus 1s, those are just my y's. So now when I differentiate this, well, it's still going to work out the same. The derivative of x cubed is going to be 3x squared. The derivative of x squared plus 1 to the fourth, or some stuff to the fourth, is going to be 4 times my stuff to the third times the derivative of my stuff, which is 2x, plus the derivative tangent of some stuff is secant squared of the stuff times the derivative of the stuff, equal to the derivative of e to the stuff is e to the stuff times the derivative of the stuff plus the derivative of sine of x is cosine of x. But look, this is really just the same thing I've written up here. This is 3x squared plus 4y cubed times y prime plus secant squared of y times y prime equal to e to the y times y prime. It's literally the same as that, just I've changed what I'm calling y.
Why wouldn't you take for 3x squared? Why wouldn't you be wanting to be 3x squared and then to the stuff of x?
Right. So I could totally do that. I could definitely say, okay, I have some stuff cubed, and I'm going to say the derivative of some stuff cubed is 3 times my stuff squared times the derivative of my stuff. What's the derivative of x?
1.
Exactly. Which is why we're not writing it, because we're lazy. We don't want to write all the things that are just times 1. So you're pointing out a really important difference in that we are differentiating with respect to the variable x. So when we differentiate things that just have x's, we just treat them normally. We're like, oh yeah, the derivative of x cubed is just 3x squared. But y is a function of x, so it's acting like some stuff that really isn't right? It isn't just like x. It is some function of x that is usually, we're thinking of it being more complicated, like x squared plus 1. When we differentiate some stuff to the fourth, you get 4 times your stuff to the third times the derivative of your stuff. So again, for all of these implicit problems, we're always going to be working in the context that x is your variable that you're differentiating with respect to, and y is implied to be a function of x. It's always going to be the assumptions we are making. So that when you differentiate something with just x's, you just do it normally. And when you differentiate something with y's, you always have to think of the chain rule that, oh, after I differentiate this thing with y's in it, I have to multiply by the derivative of the inside, which is just going to be y prime. Okay. So then the rest of it is just terrible algebra. I want to erase this bottom part here, but I want to make sure no one has any more questions about it before I erase it.
I have a question.
Go ahead.
Where did the x squared multiplied by 1 come from?
X squared multiplied by 1.
Or plus 1, sorry.
I made it up. I was just like, so when we do this, it's implied that y is a function of x. And I just said, let's just say, for example, that y was actually a function of x. It was x squared plus 1.
Oh,
okay.
okay.
I totally made it up, right? It wasn't like because we know something extra. No, I was just like, here's a thing y could be if it's a function of x.
Got it. Thank you.
You're very welcome. That's a very good question. Yes, for sure. All of it, yeah. Other questions about what's happening here? Okay. So I'm going to erase this part down here. The rest. So again, we've done the hard part of differentiating both sides. The rest of the work is algebra, which maybe sounds easy, maybe it doesn't sound easy. So the idea is we're going to solve for y prime, right? Because we're trying to find the derivative, and we're going to collect all the y prime things on one side, and the rest of the things on the other side. So I want to do as little movement as possible, really. So I'm going to bring the y prime terms to the left and the not y prime terms to the right. So I'm going to have 4y cubed times y prime plus the secant squared of y times y prime minus e to the y times y prime equal to cosine of x minus 3x squared. So bring all the y primes to one side, all the not y primes to the other side. Second step, or the next step, I should say, right? The first step was to differentiate both sides. The second step was to collect the y primes on one side. The third step is going to be to factor out a y prime from the side that all the y primes are on. So I write this left-hand side as y prime times 4y cubed plus secant squared of y minus e to the y equal to cosine of x minus 3x squared. Finally, the last step to solve for y prime is to divide by all of this that's multiplying by y prime. So y prime is going to equal cosine of x minus 3x squared divided by all of this. 4y cubed plus secant squared of y minus e to the y. And that's our answer.
I'm a little confused on like the when you got the y prime and then the parentheses, the 4y3, like that part.
So all I did here was essentially I'm dividing out, right? Saying, oh, each of these terms have a y prime. So I'm factoring that out or dividing it out. So if I write it like this, right, I could multiply it back and distribute it back through. So this would be the same as saying I can multiply the y prime by each of those three terms.
Yeah, okay, I see it.
But we have, so the thing is we have to do that though, because again, right, we are trying to solve for y prime, so we have to get y prime by itself. And the only way we can do that really is to factor it out from all the terms that have it, so that none of them have it anymore, and then get our answer as y prime equal to some stuff. And the answer should be y prime equal to some stuff, and there should not be any y primes in our answer. Okay, let's look at another example. let's do the following. I want to find y prime for the following. X cubed y squared plus 6 equal to cosine of x plus y. All right. So again, we're going to differentiate first. So when I differentiate x cubed y squared, I have to use the product rule. So the derivative of x cubed times y squared is going to be derivative of the first thing, which is 3x squared, times the second thing, which is just y squared. Right? Derivative of the first thing, leave the second thing alone, and then flip it. Leave the first thing alone, multiply by the derivative of the second part, and the derivative of y squared, or the derivative of some stuff squared, is 2 times my stuff times the derivative of my stuff. Plus 0, right? The derivative of 6 is 0, equals derivative cosine of x is negative cosine, negative what? Negative sine of x, plus what's the derivative of y?
Y
prime.
Right. So the derivative of y is the derivative of y. Right? Right. You can also say it's right. You can say, oh, I've got the derivative of some stuff. Derivative of some stuff is 1 times the derivative of stuff, which is still just the derivative of stuff, which is y prime. So whenever you have just a y by itself, you're like, oh yeah, the derivative of y is just y prime. But you can also say it's 1 times y prime if you want to be chain rule about it. And then same thing as last time. We're going to group the y primes on the same side. Doesn't matter which side you pick. If all of them happen to already be on one side, I usually just leave them on that side. But since it's kind of spread out, I'm going to bring them all to the left. So I'm going to rewrite this as 2x cubed y times y prime minus y prime equal to negative sine of x minus this 3x squared y squared. And then I'm going to factor out the y prime, or divide out the y prime. Right? When you're factoring out, you're just dividing each term by y prime. So 2x cubed y times y prime divided by y prime is going to be just 2x cubed y. And y prime divided by y prime is just going to be 1. Equal to the same stuff over here. And then divide by this. So that y prime is equal to that. Negative sine of x minus 3x squared y squared over 2x cubed y minus 1. And almost never will you be able to simplify this any further. Occasionally, you'll get something kind of special where you can factor out like some constant from the top and the bottom and cancel it. But usually there's nothing that really factors and cancels. So typically once you get to this place where you've divided, you're like, I'm done, that's it, call it quits.
I have a question.
Go right ahead.
For the second step, why did we take the derivative of x cubed and not of y squared? Like, why wasn't it 3x squared multiplied by 2y?
Well, so one would be 2y prime, right?
2y prime, yes, correct.
But the reason is because of the product rule, right? So for this here, this is x cubed times y squared, which we're thinking of as like f of x times g of x. And the derivative of that, right, we take the derivative, we have to use the product rule, and the derivative of the product rule, or the derivative of product says we get the derivative of one part times the not derivative of the other part plus the not derivative of the first part times the derivative of the second part. So really, all of this here, that's the derivative of x cubed times y squared.
Got it. That makes sense. Thank you.
Well, yeah, so be on the lookout though, because definitely most teachers will certainly ask implicit problems where you have to use the product rule. Quotient rule is less likely because it already is kind of gross enough without throwing a chain rule in there, but it is, I suppose, technically possible. Okay, let's look at another one. Let's look at this. Let's look at a slight variation on the theme. So instead of just finding the derivative for this next one, we're going to be asked to find the slope of the tangent line. So find the slope of the line tangent to the equation x squared plus xy plus y squared equal to 3 at the point 1, 1. And so we're going to start off as usual. We're going to take the derivative of both sides. So taking the derivative here, the derivative of x squared is 2x. Derivative of xy, I'm going to have to use the product rule, right? Because one function times another function. There's no way to simplify that. Yeah, Karen, to answer your question, yes. So every place where you take the derivative of y, you essentially also multiply by y prime is what I would say. So for the derivative of xy, it's going to be the derivative of x, which is not x, the derivative of x, which is 1, times y, plus x times the derivative of y, which is y prime. Right? The derivative of y is the derivative of y. And again, I'll make it very clear, right? This here, right, that is the derivative of this whole part of the xy. And then the derivative of y squared is exactly 2y times the derivative of y. Whereas I am still saying in my head, the derivative of some stuff squared is 2 times my stuff to the first times the derivative of my stuff. Equals the derivative of 3, which is 0. Be careful. I see a lot of people accidentally leave it still as 3 on the other side because they're like, oh, it's just a constant. No, derivative constant is 0. Okay, so we have choices here. One thing we could do, which I don't want to do, but I'm going to do, is we could solve for y prime just like before. We say, okay, I've got, let's see, here are my y primes, right there, and right there. I'm going to leave those on this side. So x y prime plus 2y y prime equals, I'm going to subtract 2x, and subtract y. Factor out the y prime, so you get y prime times x plus 2y equals negative 2x minus y. And finally divide by this. Y prime equals negative 2x minus y over x plus 2y. And then plug in the point 1, 1. So y prime evaluated at 1, 1 is going to be negative 2 minus 1 over 1 plus 2, which is negative 1. Perfectly fine way of doing it. It's also probably more work than we actually have to do. Here's the thing. If you're ever doing implicit and they're asking you to find the slope of a tangent line and not actually the derivative everywhere, right? So we found the derivative for any x and y, but they only asked us to find the derivative at the point 1, 1. So instead of actually going through the algebra of finding the derivative y prime in terms of x and y, after you've differentiated both sides, you can go straight to, I'm just going to plug in 1, 1 now, and then solve for y prime. Right, so when I plug in 1, 1, I'm plugging in x, y equals 1, 1. So I'm plugging in 1 for x and 1 for y and solving for y prime. So 2 times 1 plus 1 times 1 plus 1 times y prime plus 2 times y prime equals 0. That seems like a lot less algebra to have to deal with, right? Now I can just say, okay, 3y prime, I should say 3 plus 3y prime equals 0. So 3y prime equals negative 3. So y prime equals negative 1. I feel like that's a lot easier. The thing I will warn you against is that if they're actually asking you to find the derivative everywhere, you can't do this, right? You have to find y prime in terms of x, y. But if they're only asking you to find the slope of the tangent line at one point, then you can totally do this. And it's usually quite a bit easier. Let me show you one more example. Let me look at this example here. That's fine, okay. So let's say I have a function, what do I got here? Sorry, let's do, 1 second. Right, x minus 4y to the third. Let's do x squared minus 4y to the third. Yeah, that should be fine. Okay. Plus sorry, I have to, 2, 1, okay, yeah. Sorry, one second. X squared minus 4y to the third plus y to the fifth equal to x, y, sure, minus 1. That seems good, right? Let me just check one thing. 0, 1, 2. Yep, cool. All right. And the only thing I'm checking for myself is that these, so here's the thing I want to ask. I want to find the equation of the line tangent. Yeah, we're going to find the equation of the tangent line at the point 2, 1. And I was just checking in my head to make sure that 2, 1 was actually a point. Right? If you plug in 2 for x and 1 for y, you get 2 squared minus 4 times 1. 4 minus 4 is 0. Plus 1 to the fifth. So the left side is 1. And the right side is 2 times 1 minus 1, which is also 1. So the left and the right hand side are equal to each other. Sometimes someone will give you an equation, they'll pick points that actually aren't points, but it's not really a big deal. I mean, it is a big deal, but it's not that big a deal. Okay, so we're going to do the same thing we did previously. We're going to take the derivative of both sides, and we're going to immediately plug in the point to find the slope of the tangent line. So take the derivative, to differentiate. I'm going to get, so the derivative of some stuff to the third is 3 times my stuff squared times the derivative of my stuff. So the derivative of this inside stuff, so the derivative of x squared minus 4y, the derivative of x squared is 2x, the derivative of minus 4y is minus 4y prime. Plus the derivative of y to the fifth is 5 times my stuff to the fourth times the derivative of my stuff. Running out of room. I think I can make it fit though. The derivative of x times y, product rule again. Derivative of x is 1, leave y alone, plus now leave x alone, and the derivative of y is still the derivative of y, which is y prime, minus 0, because the derivative of 1 is 0. Okay, questions here before I plug in. Okay, so I'm going to plug in x equals 2 and y equals 1. So I'm going to get 3 times 4 minus 4 squared. You know what? I might as well not even write anything there. Because 4 minus 4 is 0. 0 squared is 0. And 0 times anything is going to be 0. So I could do that, but I just know all of this is going to be 0. Plus 5 times 1 to the fourth times y prime equal to 1 times 1 plus 2 times y prime. Right, this is a big 0, which means all of this goes away. Which happens a lot. People often, I designed this one specifically so that the part that was kind of gross would just be 0 when I took the derivative. So what am I left with? I'm left with 5 times 1 times y prime equal to 1 plus 2y prime. Subtract 2y prime from both sides, so I got 3y prime equal to 1. Divide both sides by 3. Y prime is 1/3. So there's the slope of my tangent line. Find the equation, I would take my slope and my point and use the point slope form. I would say, okay, my equation is y minus 1 equals my slope times x minus 2. And I would leave it like that, but if you had to solve for y, you certainly could. You could write it as y equal to, distribute the 1/3, so you get 1/3 x minus 2/3, but then you're going to add 1 to that, so you're going to get plus 1/3, because 1 plus negative 2/3 is 1/3. That's how you do that. And that's most of what we've got when it comes to, sorry, I keep trying to use the mouse that doesn't want to work for some bizarre reason. Like, what's wrong with this mouse? Why don't you want to work? Anyway, that's most of what is happening with implicit. Usually you've got some equation with x's and y's jumbled up together. You differentiate both sides, and then the rest is just doing the algebra of solving for y prime. That's kind of it. So we still got 13-ish minutes. Let's do 1 or 2 related rates problems. Related rates, also just the chain rule. It's a lot of chain rule. So let's look at this setup. The radius of a circle is increasing at a constant rate of 2 inches per second. So I'm just going to write down kind of this stuff. So the radius is increasing at 2 inches per second. At the instant, the radius is 5 inches. So when the radius is exactly 5 inches, how fast is the area changing? Okay, so there's a number of ways of trying to tackle related rates problems. I'm going to try and break it down into the process that I think that works really well all the time. The first thing I usually do, if it makes sense to, is to draw a picture. Here, the picture is probably not super useful, but I'm still going to draw it because I like drawing circles. There's my circle, and it's got a radius, and the radius is increasing, right? So later on, when the radius moves out, to here, the circle is going to have gotten bigger. Okay, so the first thing I typically do in a related rates problem is, after drawing the picture, I should say, is, as my math teacher said, identify the d-whats. Or in other words, identify what's changing. Specifically, the things you were told that are changing a certain way, and the things that you want to know how they're changing. So we are told that the radius is changing at a rate of 5 inches, 2 inches per second. So I'm going to write that as dr dt is equal to 5 inches, 2 inches per second. Holy smokes, come on. I know how the radius is changing as time is changing. It's changing at a rate of 2 inches every second. I also know I'm trying to find out how the area is changing, right? That's what the question is. How fast is the area changing? So I'm trying to find what dA dt is. That's what I want to know, the rate of change of area with respect to time at the moment that the radius is 5 inches, but we'll worry about that later on. Okay, so after you've identified the things that are changing, you typically want to find an equation that relates them. And I should be a little more specific. You want to find an equation that relates the non-time variables. In this case, the things that we're looking at are the area and the radius. Do we know an equation that relates the area of a circle to the radius of the circle? Of course we do. It's very well known. The equation is that the area is equal to pi times the radius squared. Now, I want to point out, area and radius are both functions of time, right? They depend on how much time has elapsed. So when I differentiate both sides, I'm really going to be taking the derivative implicitly, where just like before, right? When the derivative of y to the fifth was 5y to the fourth times y prime, when I take the derivative of r squared as a function of time, its derivative is going to be 2r times r prime, the derivative of r. So let's differentiate both sides. The derivative of a is just the derivative of a, right? When you differentiate a single thing, even if you don't know what it is exactly, right? Just like the derivative of y was y prime, the derivative of a is going to be a prime. But I'm actually going to prefer to write it using the Leibniz notation. So I'm going to say the derivative of a is dA dt. The derivative of pi times r squared, well, constant multiples get to hang out. And the derivative of r squared, or some stuff squared, either using the chain rule or implicit, really they're the same, is 2 times my stuff to the first power. I'm not going to write the first power times the derivative of that stuff, which is dr dt. This should always happen, right? If you find an equation relating the variables and you take the derivative of both sides, the derivative that you want to know should show up, and the derivative that you already know should also show up. So that then you can substitute the values in for those. So after we differentiate both sides, then we plug in what we know and solve. I don't know what dAdt is. That's what I'm trying to solve for. But here I have 2 pi. I do know what the radius is. The radius is 5 inches, right? We were asked how fast is the area increasing when the radius is 5 inches. And I know that dr dt, the rate of change of the radius, is 2 inches per second. And then I multiply it all out. I get 2 pi times 5 times 2. That's going to be 20 pi. So I get 20 pi. And look, the units make sense. I get 20 pi, and the units are inches times inches divided by seconds. So inches squared per second, which is definitely how an area should be changing, right? Some measurement of area, inches squared per subunit of time, seconds. So that's the idea. You ask yourself what's changing, both what am I told is changing, what do I want to know is changing. I find an equation relating those things. Then I differentiate both sides. Then I plug in what I know and solve for what I'm trying to solve for. Let's look at another example. Unless there's, I should say, are there questions about this before we look at another example? Okay, let's look at one more example. We can definitely do more examples of this next week because they're definitely harder examples, but let's look at this next one. Gabriella is standing 6 feet from her little sister, Mia. So I'm going to draw a picture instead of writing all this stuff. So here's Gabriella, and here's Mia, and they are standing 6 feet apart. Okay. Mia is holding a balloon, but accidentally lets it go. And it starts rising into the air at a constant rate of 2 feet per second. So we've got this balloon, it's going up. At a rate of 2 feet per second. And the question is, how out, so I should say, I'm gonna write the rest of this. So after 4 seconds have passed, so I should say 4 seconds after she released the balloon. How fast is the distance from Gabriella to the balloon changing? So the thing here that I didn't really say last time, but which is super important, is that when you're setting up your picture, it's really, really important to label things with variables if they're changing or with constants if they're not. So, right, this side here between Gabriella and Mia is 6 feet. That's not changing. This length here is definitely changing. So I'm going to call it a variable. I'm going to call it probably h. I like h for height. You can also use y. I mean, you really can use anything you want, but often for a vertical distance, we use h or y. That's pretty typical. And then I'm being asked about this distance here, which is also changing, right? Because as the balloon gets higher, and once the balloon's up here, that distance has definitely increased. So I'm going to call that, I don't know, I usually call it s. S is a typical letter for a diagonal distance. Almost no one ever uses d. Okay, so I've set up my picture. Now I'm going to first write down what do I know is changing and what do I want to know is changing? Well, I know how the height is changing. The height is changing, so dh dt, right, the rate of change of the height with respect to time, is 2 feet per second. And I would like to know how this distance is changing. I'm curious about how the distance between Gabrielle and the balloon is changing with respect to time. That's what I want to know. All right, so then after we figure out what we know and what we want to know, we try and write an equation relating the non-time variable. So I want to write an equation relating the variable h and the variable s. And that's how I'm going to look back at my picture. In this case, what kind of equation could I write relating h and s? I could use the what theorem? I didn't quite hear you, but I'm pretty sure you were trying to say Pythagorean.
Yeah.
Yes, would definitely. So it's going to be, so remember, for the Pythagorean theorem, the side that's the longest, aka the hypotenuse, is always the one that's by itself. So it's going to be 6 squared plus h squared equals s squared. Okay, now we're going to differentiate both sides. Okay, what's the derivative of 6 squared?
0.
Thank you, yes. I was trying to trick you guys, but you didn't fall for it. Because then you'll be like, oh, the derivative is 2 times, no, it's 0. Derivative of h squared is, derivative of stuff squared is 2 times my stuff times the derivative of my stuff. I should really say 2 times my stuff to the first, right? Because the power is 1 less. Equal to derivative of s squared, which is also going to be 2 times my stuff to the first times the derivative of my stuff. And now I'm going to erase those first powers because I don't really need them. All right, so now we're going to plug in what we know and solve for what we don't. So again, I'm trying to solve for this, right? That's what I want to know. Typically, you should be able to plug in for every other thing that you don't know. So let's see. Do I know h? Well, kind of, right? I don't know it right off the top of my head, but if I read the question again, we're saying we're looking at the moment 4 seconds after she released the balloon. So if 4 seconds have gone by and the balloon rises at 2 feet per second, how high is the balloon? My favorite number, it's 8 feet, right? 2 feet per second times 4 seconds is going to give you 8 feet. On the other hand, what about s? Well, that's a little trickier, right? We're looking at the moment when h is 8 feet, and this is 6 feet. So I guess we could use the Pythagorean theorem to figure out what this third side is. So here's the thing. People will often design these problems so that the numbers are nice. I imagine you guys know about the 3, 4, 5 Pythagorean triple. Well, this triangle is just that triangle times 2, right? The sides aren't 3, 8, 5, they're 6, 8, 10. So you could just say, oh, I have a Pythagorean triple, I know S is 10. Or you could use the Pythagorean theorem. Okay, 6 squared plus 8 squared equals s squared. That's 36, that's 64. So they add up to 100, which means, oh yeah, s is 10. That's another way you could do it. Either way, we get 10 for s. And we know that dh dt is 2 feet per second. So I know we're just about out of time here, so let me just finish the problem. So what do we get? We get 2, and usually I don't write the units in, like I just fix the units at the end. I'm gonna write them in here. So you get 2 times 8 feet times 2 feet per second equal to 2 times 10 feet times ds dt. So divide both sides by 2. 8 times 2 is 16. Divided by 10 is 1.6. And the units are going to be feet times feet per second divided by feet. So you're just going to get feet per second. And normally what I would do is I would just do the numbers. And then at the end, I would say, well, I'm talking about how a length or a distance is changing. So the units should be unit of measurement, feet, divided by unit of time, seconds. Usually I just fill in the units at the end. But that is how you would do a problem like this. So this is the usual process. Draw a picture if it makes sense to you. Figure out what's changing, both something that you're usually told is changing and something that you want to notice how it's changing. Find an equation relating those variables. Differentiate both sides. And then using implicit / the chain rule, right? Same thing. And then after you differentiate both sides, plug in the things you know, solve for the thing that you want to know.